Now it's
They
time
already
to move on to the second session of today's FDP, where we are going to learn about how quantum computing breaks classical encryption. On behalf of organizing committee of FDP and KMIT, I invite the speakers, Mr. N. Suryaprakash and Mr. S. Subhoj Kumar, to enlighten us with their expertise. Now I request Ms. Deepthi, Assistant Professor, Department of CSC and KMIT, to introduce the speakers.
Good afternoon, everyone. It is my honor to introduce our first guest speaker, Mr. Suryaprakash Nelluri, Senior Vice President in Cybersecurity at a leading global financial institution based in Texas, USA. Mr. Nelluri is a globally recognized cybersecurity executive, independent researcher, and keynote speaker with over 2 decades of expertise in application security, DevSecOps, and secure software architecture. Throughout his career, he has spearheaded critical initiatives in software supply chain security, threat detection, and secure by design practices, shaping the way enterprises safeguard their digital ecosystems. His research spanned advanced topics such as AI driven security, zero trust models, and quantum resilient cryptography, enabling organizations worldwide to prepare for the next era of cybersecurity challenges. Beyond his professional achievements, Mr. Nalluri is also an open source contributor, mentor, and a passionate advocate for nurturing the next generation of security leaders. We are privileged to have him with us today. Please join me in giving a warm welcome to Mr. Suryaprakash Nelluri. Now, I would like to welcome our second guest speaker, Mr. Subhoj Surapaneni, a dedicated security engineer at Tata Consultancy Services based in Texas, USA. Mr. Surapaneni brings more than 6 years of hands-on experience in application security, specializing in web application, penetration testing, and ethical hacking. He is recognized for his expertise in identifying and mitigating vulnerabilities, and he holds prestigious certifications including GAP Web Application Penetration Tester and Certified Ethical Hacker. Beyond his professional role, he is an enthusiastic CDF player and a nature lover who enjoys hiking elevated trails and participating in challenging Spartan 10K obstacle marathons, a true reflection of his passion and perseverance. We are delighted to have him with us today. Please join me in warmly welcoming Mr. Subhoj Surapaneni.
Hi guys, hope you're all doing well. So good evening to everyone, and it is an honor for me to talk about RSA in general and how it is being targeted by quantum computers and Shor's algorithm. So stick around for the ride. Let me share my screen. Give me 1 second. Are you guys able to see it?
yes, sir, Subhoj.
Okay.
మేడం తొందరగా వెళ్తాది.
Okay. A small disclaimer saying that we're not experts in quantum computing in general.
అంత తొందరగా పోదామంటది ఏంది తల్లి?
Dear
Excuse me?
participants, please mute.
Okay, moving on. So it is a small disclaimer just to show that, say that this research or anything that we present is not part of our, not coming from our employer's perspective. This is just our independent research and it does not affiliate with them. And we're not experts in quantum computing. I know Vishnu has delivered a fantastic speech earlier where he demonstrated a lot of in-depth knowledge of quantum computing, but yeah, we're not on that level yet. This particular thing piqued our interest, so we decided to check that out and present it in a way that mostly highlights of everyone else who has described earlier in their sessions. So please bear with us. Hopefully, we'll give you some sort of interest in getting to know a little bit of quantum computing. Okay. Let's start with cryptography, right? So what is it? It is believed to start during 1900 BC, where Egyptians have started to carve tombs based on some unknown scriptures, so that it is left to interpret for common public who come across these tombs to have their own message or interpretation on what's going on, what the original senders are trying to represent. So they started to say this and then have their own depictions. So this art has made its way through medieval times and through world wars and all the way to modern ages through various forms. So in world wars, they have encrypted messages and deciphered them or decrypted them, and then to have the message across the board to deliver it so that the eavesdroppers or middlemen cannot know what's going on, especially the enemies. So a simple way to describe this cryptography is a message where only authorized people can view and reply back. So this particular process is to convert the plain text into a ciphertext using a key and then, vice versa. So sometimes it could be the same key or it could be a different key. It depends on how important the context is, and we'll get to know more about it in the next slides. So again, this is mostly you would see this as general topics. So again, please bear with me. The pillars of modern cryptography, as we see or use nowadays, is symmetric and asymmetric ones. So a symmetric one is to simply put together. It says that you're going to use one single key. You generate one single key, and then you deliver it across to the end user. So the initial sender takes a plain text, and then they convert the plain text into a ciphertext using the secret key. And the same key is distributed in an insecure medium or secure medium, and then it's been decrypted back to plain text. So it has its own advantages and disadvantages as normal. So as you can see, as in the advantages part, the computation itself in generating just one key is easier, and it requires less power. And it's easy to encrypt and decrypt bulk data as well. So if you have large amounts of data that you want to send across, then yeah, this would be an ideal solution, but also in an insecure way. So yeah, scalability issues wise, if you have about like 50 or 100 different users that you're trying to communicate with or send a message across, then you might have to generate 50 to 100 different keys. And then you have to make sure that you're delivering these data to the right person who holds the right key. So you can see the issue here where you have to generate some sort of way where you have to have more computational power. So the examples that typically do this process is the data encryption standards and the advanced encryption standards that are currently in place. So these play a role, but they play a role in a different way. You're not going to use it for every single thing. That we will check it out later. So coming to asymmetric cryptography, you can notice that we are using two different keys. One is the public key and one is a secret key. And also, by the way, symmetric cryptography is also called as a secret key cryptography, and the asymmetric one is called public key cryptography. So both the parties are going to do the same thing, but in this case, you're going to use the public keys of the other person to encrypt our message so that this message can be decrypted by the other person's private key. Same way, vice versa. Why is this helpful? Because even if the attackers or middlemen are listening to our these are going through this network traffic, they might notice only the public keys that are available. With only just being a public key and the data, you cannot be able to decrypt the information. That is not enough. That is the reason in an insecure medium, you can still be able to exchange keys and then transfer data so that even if the attackers can see it, it's not going to have much of an impact. So that is one of the pro. And the second one is it's scalable. You don't have to generate 100 different keys to talk to 100 different people. You're going to have a public key that is available, and then you generate your own public key and then you talk to that. That's it. You're not going to work and put any extra computational efforts in order to do that part. So the other con is obviously when you're trying to implement a whole lot of security and in place, it's going to impact your performance. So it's going to take some time in generating those keys, but you lose some, you gain some. So in this way, it's performance-wise, it's a little slower, but it's efficient. Not efficient for the large data, but it's you can still uh, transfer this data using symmetry, but it's at a tunnel. That I'll cover that part in the handshake part. So yeah, the popular ones that you have in place currently today are RSA, elliptic curve cryptography, and digital signature algorithm. All right. So the TLS handshake part, famous picture, I would say. It's pretty simple to describe. I will show you how it breaks down in the next slide. But in here, you can see it's just a small representation of what goes behind the scenes of a TLS handshake. So as you can see, the exchange happens between a client and the server. So you go into your browser and then you type in google.com or facebook.com, whichever it is. You hit enter, and as soon as you hit enter, the browser acts as your client, and the Facebook server acts as your server. So it initiates starting with sending like client hello. It says I am what I am. I'm going to I have a couple of cipher versions that I would like to exchange with you, and make sure that you have appropriate ones so that we can start communicating together. So on the first arrow, you can see it sends client hello, and then the TLS version it supports or it has, and then sends to server, and then server replies back saying that the server hello, and then the appropriate versions that it can support, and then they decide upon the exchange some pre-master secret, and then they validate their identities, and then they validate identities in the first place. I should have covered that part, but yeah, they send the pre-master secret, and then the cipher exchange gets completed. And then when you see that secure connection established, that is where you have an outer layer of the asymmetric exchange. But inside the tunnel, you'll have the data exchange happening in symmetric cryptography, because that's where it's easier to encrypt and decrypt information without having to all the time go back to public key and private key decryption and encryption. So this is where it comes into play inside that particular tunnel. They both play in action or go hand in hand, I would say. You might be wondering why I'm covering this, because I want to show you I'm going a little backwards on before jumping into RSA in general on what goes behind the scenes in the network traffic. I'm not sure if you're familiar with the Wireshark. I believe some of you might be. So this picture might be pretty familiar to you on what goes on behind the scenes. So when you see in the first highlighted mark, it's a three-way handshake. So your TCP one. So it's just like a ping. You just say hello, and then you respond. The server responds back saying hello, and then you both acknowledge each other that you exist, basically. And then the second one, you say TLS handshake. Well, that's where the things happen. It's like saying officially you're shaking hands and saying, "Hey, I'm who I am. I'm browser. I'm Chrome, whatever." And then you notice these cipher suite exchanges, cipher keys exchange, everything's done, and then you notice on the 11th number, yeah, you'll see that the cipher change is completed. Then comes the data transfer part. That's where the tunnel is established. And then the inside, you see that the data 200K status code. You're not supposed to see that until you have the private key. If you don't have the private key, you're only going to see as application data, and that is encrypted. If you have the private key, that's where you can see the highlighted green ones, yellow ones in place, knowing that the actual data transfer is happening. So once everything is going good and you're completed with your stuff, data transfer and everything, the connection gets closed, and then you can see that the transfer or the connection is completed. And in the bottom, you can see the same thing. You're going to see that your connection is completed. Moving on. So these are the guys. So these are the basic standard that happens behind the scenes of before even the key exchange comes into picture, the TLS handshake and TCP and all. So moving on to these gentlemen, these people are the ones who have created the RSA key back in 1977. So it's pretty much the solid foundation of digital security for over 40 years, I would say. Yeah. And it's still holding accountable. But the thing is, RSA is in general is being depreciated in TLS 1.3 version, which I'll cover that later. But still coming into digital signatures and part, it plays a major role, and not all companies or organizations are adapting to that new environment, unless companies like Google or Facebook. But there are some companies that are still using 1.2 version and doing exchanging information using RSA keys. So coming to this slide, so what they did basically was to so they built something called something on integer factorization problem. In order to explain, I know this has been covered in depth again. This is just a high level, so please bear with me. If in plain terms to describe this, if I give you a really large number that's made by just multiplying two prime numbers, it's extremely hard for a computer to figure out what those exact two prime numbers are. Not just two prime numbers, exact two prime numbers are. So that difficulty itself is what gives RSA its strength. It could be correct, but the thing is, it could take forever. So the reason it survived so long is because of those big key sizes. So you're talking about 2048 to 4096 bits. So initially you're saying, ultimately you're saying the larger the key, the harder it is to break. So the trade-off for this, as described earlier, is the bigger the key, the bigger time to generate and then decrypt it, the computational power itself. So yeah, so as you can see on the bottom right, you see a key pair that you can generate it yourself online or in your local. I'll show you how we can generate that in local and then encrypt and decrypt it in the next slide itself. So I've done this in my local Kali Linux, where in the terminal you can use OpenSSL to generate RSA keys. So and if you noticed on the first line itself, first command, you can see that I've tried to generate 2048 bits using 2048 bits. So you generate the private key first, and then in the next command, you notice you're trying to get the public key out of the private key, because get as in you're extracting public key out of the private key so that you can use it to share across the end users in an insecure medium. So this is how a private key looks like for a 2048 bit. And the public key, if you notice it, the first couple of lines would be similar to the ones you see on the private.pem file. So displaying a plain text file. So here, as we described in the earlier slides, we're trying to show how a plain text message like, hello, my password is 123. I'm trying to put that into a text file, and then I'm trying to encrypt it using pkutil. So we're encrypting it and then saving it in the encrypted.pin file using our public key. In the bottom, if you see the cat command, that is how the encrypted with the public key looks like. So it's just gibberish. You don't know what's happening until you have a private key to decrypt it. So in the third command, you see I'm trying to decrypt it using the private key. and then I've saved it in the decrypted.txt file. So again, when you cat that out and read it out, you would see, hello, my password is 123. So you're going from encrypted to decrypted using your public and private key. So on the last but one command, if you notice it, I tried to decrypt it using my public key. So in general, if you analyze the network traffic again, you might find public key and some sensitive information, right? So when you try to decrypt it using your public key for that sensitive information, you would see that it's not possible, and then you would need a private key for that, because part of that private key is part of the encryption standard, so it's not that easy. Okay, moving on. All right. So again, this has been described multiple times, so I'm not 100% great at describing this, so please bear with me. Okay, so the math behind this RSA is complicated for me, but might not be that complicated for everyone. So you go through these three essential steps in having the keys generated, encrypting it, and then you get the outcome of the encryption as a ciphertext, and then you decrypt it back. So considering this, as you can see, the first step is generating keys. So we start by just multiplying the two numbers. Like we said earlier, it's hard to break it down later, but you can encrypt it by just choosing some two random numbers, right? So two random large prime numbers, by the way. So you multiply that, you get the modulus of n. You get the modulus n as p into q, and then you have the Euler's quotient phi of n, which is p minus 1 into q minus 1, and then the encryption exponent. So encryption exponent and decryption exponent are the key partners here that we should be analyzing a little further. So the conditions for encryption exponent to have that value is it should be greater than 1 and then less than the Euler's quotient. So I'll explain to you in simpler terms in the next slide. Hopefully you guys get it, or you might already get it. And you compute the decryption exponent D as the modular inverse. So you get the private key and then the public key, and using those, you encrypt the message M, which should be greater than 0 and less than the original number that we got. And the ciphertext formula that we use is m to the power e times mod n. And the decryption wise, you recover it back using the same formula. Not the same formula, my bad. It's m is equal to equivalent to c to the power d and times mod n. So the trapdoor part is the what holds it together. So that's the magic that's happening in there. You multiplying the primes is easy, but factoring that product back to get those primes, exact primes again, is essentially really hard for classical computers. That's the one-way door that keeps RSA secure, at least until quote unquote quantum computers come into play. So the examples is pretty simple. I've chosen two small numbers. So let's make this a concrete base, right? So you choose P as 5 and Q as 11. And then you, as described earlier, you try to compute modulus. You multiply them together. You get n as 55. And then the third part, you just subtract one number from each other and multiply them together again. You'll get 40. So now we need an encryption exponent. So it has to be relatively prime to 40. So in other words, it should not be, the remainder should not be equal to 0. So it should be greater than 1 and less than 40. So you start with 1, 2, 3, 4. Then you end up with 3 because it cannot be 1, it cannot be 2. So you end up making e is equal to 3. So the trickier part is to find the decryption exponent. So for the decryption exponent part, you have this formula written down earlier. It's just that I reversed it back to D into E. D times E is equivalent to 1 times mod 40. So when you replace E with 3, you see D 3 into D is 1 times mod 40. So I've extended that using the Euclid's algorithm on the right side. It's called the calculating modular inverse. So In order to do that, we are breaking down 40 as 3 times 13 plus 1. And then further, you're breaking it down as 3. You're breaking down 3 as 1 times 3 plus 0. So you're getting reminder 0, we're negating that. So you write it down in terms of 1. So we eventually get to the formula of 3D plus 4K. So K is just a placeholder and it does not hold a particular value. Since we are only talking about uh, 3D 40K, 3 plus 40K. So 40 into 1 and 3 into 3. So D cannot be a negative number. So we're going to have to subtract that to get 27. So when you put those values together, you're going to get the modular inverse as 3 into 27 is 81, which is equal to 1, which satisfies our condition earlier. So you get the values of public key as E is equal to 3 and private key D is equal to 27. Moving on. The encryption part. So earlier we saw the messages where you encrypt it using or you choose a number m is equal to so greater than 0 and less than n. So if you decide to go with m is equal to 9, you generate the ciphertext using the formula as shown earlier. And you divide that to get the reminder. So the reminder itself plays as a ciphertext. So now we have and ciphertext. Now we'll try to, when this message is passed on to, let's consider the classical example of Alice and Bob, right? So this message is passed on to Bob, and now Bob will try to decrypt it using this formula M, which is C to the power D mod times mod N. So the math that goes on here is little, I've written down steps that is upside down. So please follow me along. So this number 27, so we're trying to break that down into powers of 2 and adding it up. So you get 16, 8, and 2 and 1. So it comes out to be 2 to the power 4 plus 2 to the power 3 plus 2 to the power 1 plus 2 to the power 0. So when you replace those numbers and you try to calculate the mod, so you follow this path called repeated squaring. So you get those values out, and then you try to multiply all of them together. So when you notice the 14 square is 196 and how you end up with 31, simply just divide 196 by 55, and then you get 31. So that is the value. We get 31 mod 55. You follow the similar process for the other ones, and then you get the answer. And then you multiply all of them together to finally breaking it down into 9. So that is our recovered message. So common question that we might come across. So as I mentioned earlier, we're saying TLS 1.3 is no longer using RSA as a main key cipher exchange one. So why are we still talking about RSA, right? Again, still has a historical dominance where it's been a backbone of all the email, secure email for decades, and legacy systems and the protocols still rely, some of the protocols still rely on it. And some companies, not everyone has upgraded to 1.3. Trust me on this, they did not. So and the digital signatures part is also still used for the for authenticity, claiming who we are, and then we're using it to code, sign up some code, and then for digital signatures like signing on PDF and etc. And your companies and smart cards where you still log in every day using these RSA smart cards to verify your identity. And compatibility wise, again, a lot of IoT devices in the current market are still relying on RSA. So it takes a while, but it's going to slowly pan out away, I would say, but it will take a while. Not everyone likes to change rapidly, so they still follow along. So from an attacker's perspective, so we typically try to, I'm not saying we, so in general, the attackers try to use these tools in general to decipher or crack some of the weak passcodes or weak passphrases so that they can extract the private keys. Sometimes these private keys are protected by some of the weak ones. So in that way, the John the Ripper is pretty much popular and Hashcat as well. I've used John the Ripper a couple of times before. and have not exclusively used RSA CTF tool, but yeah. So all these tools that are shown here are pretty much used to extract information as much as possible. Moving on. Okay, so bear with me on this. I don't have an in-depth knowledge on what I'm about to say, but I believe I'll cover some of it. So let's now go into qubits. You might be hearing these words in 3 to 4 days, I guess, but yeah. In the classical world, all this information that we typically see is stored in bits, right? So it's pretty much simple. It's either 1 or 0. You know a definitive answer. Like in the image, you see that the 0 is completely in orange and 1 is completely in blue. So you know it's the 100% deterministic state. But in quantum, these are a little different. So they can be either 0 or 1 or just a combination of both at the same time. So that is what a superposition is. So what you're in the simpler terms, I'll show it in a different animation. But in simpler terms, the probabilities of the adding the 0 and 1 should always be equal to 1. And in a simpler way, I would also say that you can imagine it as spinning a coin. It's spinning its head and tails. It's both head and tails. But the moment you stop it and look at it, collapses into one outcome. That's how measurements work in quantum computing in general. So this is what gives the quantum computer having a multiple states at once and a very good advantage. So if you're having combining this with multiple n number of qubits, so the possibilities is 2 to the power n. So that could be represented at once, and then they can take on that many calculations as well to have results in a faster way. So that's why it matters for encryption. So when you're trying to factor a large number in RSA, the classical computer has to check possibilities one by one. You're eliminating one factor and trying to do it one by one in a pace, right? In a quantum computer, using this superposition, you can test many possible factors at one single time. Okay, so we're still relying on classical gates, right? So you're trying to cover this in a very slight manner. So all these classical gates still operate on bits, which means again the input is always a 0 or 1. Output is also a definitive 0 or 1. So it's pretty much deterministic. So as you can see with the NOT gate, AND gate, NOR gate, you have these outcomes available to you pretty deterministically. So it is the foundation of all digital circuits and processors. So when you chain all these gates together, that's where, like in millions and billions numbers, we get digital circuits. So these circuits are what make up the processors inside our laptops, phones, servers, and et cetera, et cetera. So you can think of it as a strict way to represent strict rules. So they take definitive inputs and you get definitive outputs. Now, switching on to quantum gates, they different the qubits the gates itself behave in a different way. So instead of just operating on 0 and 1, they will operating on superpositions basically, or both. You never know. So it's reversible at pretty much every stage. So as you can see from the block sphere, it represents the first animation represents the Hadamard gate. And the second one represents the right next to it represents the poly X gate. And the bottom one, I don't have a better picture of the block sphere, but just a matrix showing how it's been represented in a circuit. As you can see on the Hadamard gate, you're trying to go from 0 to 1, but instead you're curving it out. So it's going three-dimensionally. It's what puts the qubits into a superposition. So the qubit is like spread out, meaning it has equal probability of being measured as 0 or 1. So you're not letting it rest until you're just making it spin continuously. So in a way that the computations that we need happen, and then we get the final outcome. So the poly X gate is like the quantum version of the earlier, when we looked at it, it's a quantum version of a NOT gate. So it is equivalent to NOT gate and flips the qubit 0 to 1 and vice versa. So the C NOT is where the entanglement pretty much happens. So takes the qubits, flips the second qubit only if the first one is 1. I'll explain that in a better animation. Talk about entanglements and a better animation in the next slide. So let's go to that. So as you can see from this image, this represents the quantum, the power of quantum mechanics. So these two important topics, entanglement and quantum parallelism. So entanglement basically means that the qubits can be linked together in such a way that the state of one instantly influences the other, no matter how far or apart they are. So if you just put two coins together and put some magic in it, and then you throw one a coin into outer space and the other coin into another outer space, and they're like million light years away, and that magic helps you. If one turns out to be 0, somehow they're connected, and then the other one turns out to be definitely into the other state, which is 1. So that is what the magic or entanglement is about, as far as I know. Please don't quote me on it. So I've tried to understand things in a simpler way. So yeah, so the quantum parallelism, on the other hand, is it also comes from superposition. So instead of representing just one value at a time, so again, like I mentioned earlier, if you're taking 50 qubits, you're going to have 2 to the power 50 parallel states, and that is a lot. So impact-wise, these properties is what quantum computers, the potential to solve problems faster than classical computers. Factoring large numbers, searching databases, etc., and etc., or simulating molecules, that's not that possible today. So the Shor's algorithm for factoring and Grover's algorithm for search are direct application of these principles. Okay, so the image itself, you have the quantum computer at IBM that's been currently at works, I would say. So the second image, if you notice the white cylinder thing, that's what it's called a dilution refrigerator. So it operates at extremely lower temperatures at around 15 millikelvin. That's like even colder than outer space. So it uses a special mixture of helium-3 and helium-4 isotopes to remove heat in stages. So you're trying to bring it down the heat that it generates and noise, so so that it operates peacefully. The gold chandelier on the right side, it looks like a chandelier. So it has this represents the different cooling stages as well, from top to bottom. So each layer lowers the temperature further. So at the very bottom, if you notice, the qubits or superconducting circuits sit at the absolute 0, preventing thermal noise from disturbing them. So typically, if you open that white cylinder part, you would just see this part, the chandelier thing. So the golden circuits, so these are called the plates that are shown are the cables, are microwave control lines and readout writing. They connect classical electronics to the quantum chip at the bottom. So these control the qubits, so and also read out the states, that is 0 or 1. And the black cabinets that you see on the second picture, they are the control systems that interface with quantum processors. So they generate the microwave pulses, synchronize timing, and run the software stack like Qiskit. It's an open source framework, and they use AR simulators to run. We use AR simulators to run do our calculations. So in other words, the fridge keeps the qubit stable. The gold wiring talks to the qubits, and the black cabinets run the algorithms and translate them into qubit instructions. Moving on. So the algorithms, it's not just about doing the same thing faster and faster. You're making the computers think differently, right? So they rely on superposition, entanglement, interference to solve problems in way classical computers they cannot do that. So Grover's algorithm is introduced in 1996 to speed up some unsorted search problems, right? So imagine you're going through a giant phone book and you don't have any particular order to follow. So Grover's algorithm can just do that by taking a large number and square rooting that. If you're taking 128, if it takes you 2 to the power of 128 times to crack a symmetric key, you're breaking it down into a square root of 128. Wait, square root of 128. Okay, that might not be right. My bad. So you're breaking that down into basically a square root of n. So when it comes to other algorithms, Twist-Joseph was an early proof that quantum speedups are possible. And the quantum Fourier transform is a critical building block that shows up in many algorithms. So especially in Shor's algorithm. All of these have paved the way for Shor's algorithm, which is the real game changer because it takes factoring large numbers and RSA security pretty much relies on it. So yeah, that pretty much ends up my part. I will now hand it over to Surya. Please go ahead, Surya.
Yep. Thank you, Subhoj. Greetings, everyone. Let me share my screen. Hope everyone can see my screen.
Yes, visible.
Yes, sir.
Okay. Thank you. So let's Subhoj covered the basics of RSA and also like basics of quantum. I know some of these topics are already covered in detail in the previous sessions, so my apologies if I'm kind of duplicating any of the content. I know Shor algorithm is quite famous. I'm sure like it's covered in some of the other sessions as well. But like from my perspective, I will try to explain what is our understanding. As again, Subhoj mentioned, we are from the industry. We kind of try to hack things out and then use tools like to crack some of the passwords and all that. So when it comes to Shor's algorithm, that's important milestone. And let's look at why Shor's algorithm is such a milestone, right? So let's take analogy, a keychain analogy. So on the left, we have a classical computers comparison versus the quantum computers on the right, which is on the right side. So the classical computers try every possible key one by one. If we take a large keychain, they try every possible key one by one, extremely slow as the numbers grow. The times increase exponentially, which is exactly why RSA and ECC are secure today. On the right, quantum computers take a completely different approach. Using superposition and entanglement, they can effectively test many keys at once. So that means what looked like an impossible problem with classical systems becomes a solvable in fraction of time. So to put simply, classical security is built on the assumption that factoring big numbers is hard. And Shor's algorithm proves that with quantum, it's not. And that's why it directly threatens RSA and ECC encryption. So the lock and key analogy sums it up very well. A classical computer tries each key until one fits. A quantum computer, by contrast, tests them all simultaneously, and the key just opens up. Shor's algorithm and its impact on RSA. So I know Subhoj covered RSA in details. So let's look at a brief overview of how Shor's algorithm works. So Peter Shor is a mathematician who really challenged the game of quantum computing. In 1994, he introduced what's now called Shor's algorithm. This was groundbreaking because it was the first algorithm that could factor integers and solve discrete logarithms efficiently in polynomial time on a quantum computer. But why does it matter? So, well, factoring large numbers is exactly what underpins the security of RSA and discrete logarithms. They are the basis of for ECC as well. So Shor showed that if we had a powerful enough quantum computer, both of these systems could be broken. So the impact was huge. It didn't just stay in academia. The results sparked a wave of global research into quantum computing and equally importantly into post-quantum cryptography as well. Post-quantum cryptography encryption methods that can withstand the quantum attacks. So in many ways, Shor's work is seen as one of the biggest milestones in both computer science and cybersecurity history. And it's one of the reasons why the security community is racing now towards to prepare for the quantum future. So what does the Shor's algorithm do? At its core, it's designed to find the prime factors of a large number. Something that sounds simple, like if you take like breaking 15 into 3 and 5, but it becomes extremely hard when those numbers are hundreds of digits long. So RSA typically uses like pretty large number. Classical computers are very slow at factoring the large numbers, and that's why we think that current digital signature algorithms, RSA, ECC, are like secure. So Shor's algorithm really challenges the game by using quantum properties like superposition, which lets it test many possibilities at once, and a clever trick called period finding to uncover the prime factors exponentially faster. Again, to put it simply, what would take a classical computer years or even centuries could be done in hours or days on a large-scale computing machine. And that's why this algorithm is such a direct threat to RSA encryption, and because it targets the exact the hard problem RSA is built on. So in the next slide, we'll be covering, like, we'll take a toy example, like factoring 15 using the Shor's algorithm. So this it's divided into 3 steps in this case. Step 1 is all about converting factoring into period finding problem. Instead of directly trying to find a factor for numbers like such as 15 or 21, just for the use case, it's really hard as the numbers grow. We reframe the problem. We pick a random number that shares no common factor with n, and then look at repeated powers of that number, modulo n. Eventually, the sequence repeats itself at some point. So that repeat cycle is called period. So that's what is important for the next step too. Finding that period is super hard for classical machines, but quantum computers use something called quantum Fourier transform, which is basically a pattern detector. So by putting qubits into superposition, the algorithm explores many possible values at once, and the QFT pulls the hidden period for far more efficiently than any classical system that exists today. So once we have the period, it brings back to the classical math, where the period is the heavy lifting here. Once that is done, we run simple a greatest common divisor check that classical computers are pretty fast at, and that will help us to find the public and private keys. So the key idea here is that hybrid nature of Shor's algorithm, quantum power for the hard part and classical method to finish the job. So together they cracked the factoring problem in polynomial time, which is why RSA is suddenly becoming vulnerable in quantum world. So let's run through a simple example. In this case, I have taken a factor of number 15. And so far we have seen maximum 20 factor of 21 with pure quantum computing. So in this case, I took an example of 15, and let's take a random, choose a number. We have to choose a random number that's less than 15. In this case, I chosen 2. Now we repeatedly raise 2 to the different powers, each time taking the result modulo 15. So if you follow this computation, like with powers of modulus 15, we get the sequence as 2, 4, 8, and 16. So once we hit 1, the sequence starts repeating. So the length of the cycle in this case is called the period, and here the value is 4. So in the step 2, this is where the trick comes in. If the period is even, we compute GCD of a to the power of r by 2 plus or minus 1 and the number n that we wanted to crack. So when we do the computation, like the period is 4, like GCD 4 minus 1. So the GCD of 3 of 15 is 3 and GCD of 5 of 15 is 5. So we found the factors 3 and 5 with the Shor's algorithm. There are a lot of resources available online. In this case, like I have taken the the Qiskit framework, which is IBM's open source framework, and we have used Google Colab, a true platform that provides coding easy, and you don't need to worry about any hardware or software installation. So we can just rightly run the Shor's algorithm using a AR simulator that basically a Qiskit's high performance simulator, which try to mimics the quantum computer. Obviously, like we don't have access to the real quantum computer, so we kind of using simulator give us some logical results to compare how Shor's algorithm works. So the outcome that you see here is the algorithm that was able to factor 15 into 3 and 5, showing how quantum algorithms like Shor's can break down numbers much faster than classical methods. Even though in this case 15 is a simple case, the same principles scale to much large numbers, which is exactly why RSA encryption becomes vulnerable. So if you try to use the same analogy on a large number, in this case we try to run on 77, and it immediately gave out of memory error. I think for small numbers like 15 and 21, the AR simulator works fine. But as once the problem size grows, the memory requirements explode exponentially. And that's where the actual quantum hardware is needed, because classical machines can't efficiently simulate quantum parallelism at scale. So why this matters for RSA? So RSA encryption is built on one simple idea, that it's incredibly hard for classical computers to factor a very large numbers into their prime components. So that difficulty is what keeps the data secure with RSA and ECC. But Shor's algorithm directly attacks this hard problem. On a quantum computer, it can factor those huge numbers exponentially faster than classical methods. So that means, what once took like billions of years on today's computer could, in theory, be solved in hours or minutes if you have powerful enough quantum machine. So obviously, since RSA and ECC are widely used, the impact is huge. If the Shor's algorithms runs efficiently on scalable hardware. So private keys would be revealed and encrypted data could be unlocked, as Subhoj demonstrated. Once we have the private keys, we could decrypt the data. So the key takeaway is clear. RSA, the backbone of much of today's internet security, becomes fundamentally vulnerable in the quantum era. Kind of try to visualize the current situation. On the left, we've seen Shor's algorithm in theory. Shor's algorithm came in theory in 1994. We have known that with a large fault tolerant quantum computer, it can break RSA in theoretically. But on the right hand side, we can try to depict the real time situation, real life today. Current machines are small and noisy, so demonstration factor tiny numbers 15 or 21 are possible, but current RSA standards use 2048 bit, which is hard to achieve.
Yes.
So the RSA or ECC remains secure for now. The risk is long term. Attackers can harvest now and decrypt later. That's one of the risks that we have. So we're still far away, but like researchers are estimating about 5 to 20 years, but that is kind of accelerating with the AI. So the highest claimed result so far, as per the news, is the 12-digit number, but that's using the hybrid quantum-inspired annealing techniques. So we still don't have the hardware to solve it, so we don't need to worry about it at this moment. So there are limitations in terms of the hardware, and also quantum-inspired annealing, essentially classical simulations of quantum effects, is reaching much larger numbers, but that's not same as true quantum breakthrough. We cannot consider it as quantum breakthrough. And the bottlenecks are clear. We don't have enough stable qubits, and noise makes long computations unreliable. As Subhoj mentioned, the cooling and hardware wiring also creates huge engineering challenges to meet that hardware. Looking ahead, experts predict that by 2030, error-corrected qubits, quantum computers will begin tackling real-world cryptographic systems like RSA 2048. So the recent trends, these are pretty much, I came to know about it pretty recently. I think Google has released new variations of this in May 2025. So they have made one of the big shifts that we have seen on this improving Shor's algorithm. So Google's quantum AI team has shown that breaking RSA may need far fewer resources, compared to from 20 million qubits, they reduced it to 1 million qubits, and they estimated a week of runtime. It's still futuristic, but it's just a lab concept. So they also improved Shor's algorithm with smarter math, like modular exponentiation and time-space trade-off, making factoring more efficient. Along with the software, the algorithm improvements, they are also making hardware improvements. They're advanced error correction and qubit layouts with the different techniques and storage models. So in summary, this research is still evolving in terms of both algorithmic and hardware, but these are accelerating with the time. So that's why we need to kind of focus on PQC and start adopting at least the hybrid techniques. So one of the risks we have is harvest now, decrypt later. Even though we are not at risk now in terms of breaking the algorithm, but adversaries typically collect today's encrypted data, like emails, like financial transactions, medical records, or classified files. They can decrypt it at later point of time. Whenever the Shor's algorithms can break RSA and ECC. So, but it's why it's dangerous is because the problem is longevity. Sensitive data in finance, health, and national security often needs to kind of stay secure for decades. And typically, the records management keeps as classified for 10 to 20 years as such, right? So attackers only need patience, but defenders must anticipate the future breakthroughs. So for example, imagine a signed banking transaction being decrypted years later, exposing financial histories between two individuals. Or other real example could be, right now the intelligence agencies from different countries like NSA and China and Russia, FSB, are already kind of stockpiling the intercepted encrypted communications. So even if they can't break it today, once the quantum machines are available, those archives can be decrypted and exposing decades of secrets. and it poses significant threat to the nation's security as well. So that's why we need to adopt PQC. So NIST has already kind of standardized some algorithms like Kyber and dilithium to withstand some of the quantum attacks. I think the near-term approach is using hybrid combination of classical and quantum safe encryption, so that government and industries should start migrating to defend against the harvest now decrypt later risk. So just a brief timeline, just to show that how it all started. And the initial idea coined in 1981 by Feynman, the quantum computers to simulate quantum systems that classical machines couldn't. And 1994 we have Shor's algorithm, and 1996 we have Grover's algorithm, which shows that database lookups can be made very easy. And in 2019, Google also released solved a problem in 200 seconds that would take classical computers like years of work. I believe one of the other milestones, the PQC standards have been evolved, and NIST kind of finalized post-quantum cryptography as well. Like in 2030, researchers estimate that quantum will be adopted, and it could potentially pose real threat to the today's encryption. So we're not completely defenseless. So PQC comes at our rescue. So it's a new branch of cryptography focused on algorithms that can withstand quantum attacks. Unlike RSA and DCC, they are built from mathematical problems that are like hard to solve for both classical and quantum computers. The PQC kind of helps us out to withstand some of these attacks in the near-term future. So the goal is simple: make sure our algorithms and data stay secure even when Shor algorithm becomes practical on large-scale computer. So instead of factoring large numbers, PQC relies on lattice-based problems and hash-based constructions where quantum speeds doesn't help much. I think this is well explained by Vishnu sir in the previous session. So PQC gives us hope. Even in the world like powerful quantum computers, we can still secure our digital future in transactions. We use NIST a lot. Companies in the industry, they follow the NIST standards and they look forward to implement any algorithms that NIST describes. So NIST is like a US agency that sets many of the cryptography standards that are adopted worldwide. In 2016, they kind of launched a global competition to find quantum safe algorithms. And from that, they have rigorously started testing both security from security perspective and efficiency perspective as well. So the goal is simple but crucial: replace today's vulnerable systems like RSA, and with new algorithms that will stand strong against quantum computers. And this table indicates like how many billions of dollars every country is kind of investing. China is the leading investor in terms of spending, but most of the innovation comes from the US industry partners as well. EU focuses on the collaboration, and Japan has also started investing into quantum computing in billions. And they're also emerging as fast-rising player in the world. To summarize, let's wrap it up what we discussed. So we discussed about RSA and how RSA works. And RSA has been backbone for digital security for about 40 years. And it has been challenged by Shor's algorithm in 1994. And from there on, quantum picked the curiosity of the cybersecurity folks. The Shor's algorithm expected to crack these algorithm prime numbers pretty fast. So we need to adopt post-quantum cryptography. So these new algorithms designed to resist quantum attacks based on math problems quantum computers can't easily solve. So this way the NIST plays a crucial role. They are leading the global effort. Already standardized some of the algorithms like MLKEM, DSA, and SHA-based DSA as well. So the time to act is now. Waiting until quantum computers arrive will be too late because of the attackers can decrypt the harvested encrypted data at any point of the time in future. So at least the critical industries or the national security systems should be start adopting it. Eventually, I think since NIST has published it, companies are also adopting, doing research about the PQCs and started adopting some of the PQCs as well. So even though quantum is like a serious matter, like, we put together some memes that kind of exist around. It's in a funny way, right? So this one talks about the transition between distracted boyfriend qubit meme. So where qubits are not just on and off, like they can exist in multiple states at once. So the meme is funny way to show how easily distracted they can get. And the other popular theme is the bad actors BART meme theme, which indicates the Shor algorithm. So this is exactly what keeps cybersecurity experts up at night. So Shor's algorithm has the potential to break RSA and ECC, and one day it won't be a joke. Like once the bad actors crack the wall, the world's entire cryptography system will be at risk, and most of the financial along with other industries also will be at risk. I think with that we'll conclude our slides. Happy to take any questions. So if there are no questions, hand over to Kishore sir.
Okay, Surya.
Thank you all for giving the time and opportunity to present in this platform. Thank you all.
Thank you guys. Have a good one.
Dear participants, if you are having any doubts, you can ask. Thank you so much, Mr. Suryaprakash and Mr. Subhoj Kumar, for the insights you provided. Your contribution to our FDP was significant and we are grateful for your participation. We have covered concepts including pillars of cryptography, symmetric and asymmetric cryptography, SSL and TLS handshake, RSA, Shor's algorithm, step-by-step explanation, RSA quantum threats, and all are interesting. Once again, thank you for your time, effort, and expertise. We hope to have the opportunity to work with you again in future. Thank you so much, sir. So we are going to take a 10 minutes break. Meanwhile, you can fill the session's feedbacks. And in 10 minutes, we will again start the third session, the last final session of the FDP.